All right, thanks to the session chairs for introducing me and for the conference committee for inviting me. So today, my talk is not on inertial sensors, but hopefully that won't scare anyone away. If you do leave quietly. Anyway, so I am going to talk about something that's relevant to, I don't know why this isn't advancing. So today I'm going to talk about something that's very relevant to inertial sensors, and I have worked on some inertial sensors in the past, and so I'll try to make a couple of parallels today. But I'm going to talk about some interesting effects of using nonlinearity. So rather than ignoring nonlinearity, we're going to use it. And the device that I'm going to discuss and the application that I'm going to discuss today is on resonant mass detection. So it kind of follows along very well from the plenary discussion this morning. And so I'm going to discuss resonant mass detection, which is a different technology, but for the same type of application, explosives detection and other types of detection. I'll show you some. So I'll discuss the mechanism, then discuss some examples on experiments we've been doing with DNT, and then I'll talk about some new things on how you can further use nonlinearity to improve the sensitivity of the devices, and then finally conclude. So just as a refresher, thankfully we had a plenary talk on this, on mass detection this morning, but in linear resonant mass detection, the easiest way to think about this is just to think about a cantilever. If you have a vibrating cantilever and you change the mass, the frequency shifts. And so traditional mass detection is done that way. And you can see if you add mass, for example, the frequency curve will shift here from this curve to the resonant frequency will go down, and you can detect that. It works really well if you have a very high Q oscillator, but in environments of air or in liquids, it doesn't work very well. Some people have gotten around that. For example, this picture is from Scott Manalis. They've developed an interesting technology a few years ago where they built the fluidic channel inside a cantilever and then vacuum packaged it to get a high Q device and still be able to do measurements in liquid. But again, that's for very specialized measurement technique. So what I want to talk about is a different sensing modality. So let's say you have a cantilever just like the one in before, but we're going to add some nonlinearity to the cantilever. Cantilever by itself has a little bit of nonlinearity, but is in general a relatively linear device. So we can do that by just, instead of making it a cantilever, just fixing it at either end and making it a fixed beam. That means as it stretches, the axial, the length of the beam has to stretch, and that creates a cubic nonlinearity. And so additionally, if you have a drive technology to make the device resonate, for example, a parallel plate capacitor, this is a really simple one. There's many ways to do this, but what we're trying to achieve is state-dependent actuation. So a parallel plate capacitor, a Lorentz force capacitor, a magnetic drive, these all have the unique property that as the device moves, as you apply, say, a voltage here, and this beam bends down, the force changes, right? It's not a constant. It's not just time dependent. It's time and position dependent. And so that leads to, I'm not going to talk about math too much in this talk. This is it. So get a good look at this one equation if you like equations, or wake up if you don't like equations. This is the one equation, but you'll see that it looks very different from a harmonic second order lumped mass differential equation. So this one has a unique, the forcing function is dependent on position. And that's true for anything with what I call state-dependent actuation, where the force changes with the position of the device, of the beam. And so what this leads to is a unique condition, which is called parametric resonance. And the easiest way to think of this is to think of a kid on a swing. The way that a child builds up, it leads to, in the dynamic space, instead of having one nice resonant frequency, now it has a whole bunch of tongues. So one resonant frequency would look like a line in this space. But instead, now we have all these spaces where you can get unstable or large amplitude behavior. And we can use that for sensing. You can understand that the same way you understand a child swinging on a swing. If a kid, to build their amplitude, they sit up when they're in the middle of the cycle, and they lean back when they're at the edges of the cycle. What that essentially means is that they're modulating the center of mass twice per cycle in order to build up amplitude. That's the same thing that happens in that equation that I showed you. When you drive the system at twice per cycle, you're essentially in this region here, which is the center of this, what I call this instability space. And so what that leads to is some really unique behavior. And these are the kind of behaviors that I'll show you. The movie isn't playing because, of course, I have a Mac and this is a PC, and QuickTime movies don't play properly. So you're going to have to use your imagination. So anyway, this is an experimental map of one of those instability spaces. And what happens when you say, I'll just talk about this one line here, this line marked C. If you sweep across in space, you get nothing, you get no motion at all, and then you hit this boundary and you get a large motion. There's a sharp transition between no motion and motion, and then you move through this space, and when you hit this point, it snaps off, and then you get no motion again. So there's this band of actuation. When you sweep back, the same thing happens. And in a more complicated case, if you have a nonlinearity, over here you get some hysteresis. But these sharp transitions are really attractive from a sensing point of view because, as you know, when we build sensors, sharp things give us pause. They make us want to utilize them. We like to eat. Sharp things are easy to detect from a detection point of view. The other interesting thing is that damping has a very different effect in these kind of systems, which can make them more useful in environments like air and possibly fluid. So when you drive this device, this is in air, this is at a 10 torr vacuum, this is at a 10 millitorr vacuum. So essentially I'm changing the quality factor of the device by changing the environment it operates in. And notice that this is just a time trace of the signal. So the oscillation builds as you cross this boundary. The oscillation builds and then it equalizes out to approximately the same amplitude. This one is so high quality factor that we haven't seen the other oscillations die out, but they all end at approximately the same amplitude. So damping does not depend, the final amplitude does not depend on damping like it does in regular linear oscillators. So how to use this as a sensor? So instead of detecting shifts in the resonant frequency peak like in a normal system, we're detecting shifts in this instability space, or namely shifts in one point on this instability space. And so how is that different? So we've spent quite a long time in my lab looking at the best way to measure this and how it's different from linear systems, both from an analytical point of view as well as from an experimental point of view. But really, you're trying to drive the device and be able to sense the position of this and correlate that back to the mass. And so when you sweep this, because of the hysteresis that naturally occurs in some of these systems due to nonlinearity, basically what we started out doing is starting out here and literally doing a loop where you step down in frequency. When the device snapped on, you recorded that, and then you just continued doing a loop. So that takes time, right? So for a true sensor, you want to do things, you want to have the measurement happen as fast as possible. So doing this loop wastes time, essentially. So I'll talk about how we solve that problem later. But now I want to skip over. Now that you understand the technique, I want to show you some of our results. And what we've been doing is working with the ARL, Army Research Lab in Maryland, on explosives detection. So this is the detection that the Army currently uses things like dogs for, or other large systems that tend to take a significant amount of time. It's a similar system to the one that the plenary speaker talked about this morning. A very nice system. Again, it's a relatively large device, but it has high sensitivity. Just as a small aside, I saw the best the dog sensor in the airport last evening. when I got in, and my flight got in late, and there was one of those little trained beagles running around the airport. And that dog, I own dogs myself, so I'm always interested in watching these little dogs do their thing. And this beagle was the best one I'd ever seen. He was very direct, and he ran right up to someone and alerted. And when a beagle alerts, when they sense something, they sit down. And this dog sat down, and he was just shaking because he was so excited that he had found something. And so the handler goes up, and she taps the guy on the shoulder, and he looks all nervous. And she takes apart his whole backpack. And in the bottom of his backpack were 2 apples. Boy, that dog was excited. And it was excited because it got like a little piece of hot dog or something for finding those apples. But again, my takeaway from that was, well, we still got a lot of work to do. That none of these sensors we're building are cool, and they're very highly sensitive, but they don't work that well. Okay, I can say the detection is sub ppb, and I'll show you our results. But I've got to say, we've got to work harder to get closer to that beagle because the dog was still doing it. Although in the Army, out in the field, when you're detecting explosive, we don't want to put dogs out there. All right? We want the sensors to work, and we don't want to put life in danger, whether it's animal or people. So anyway, so this is a technology overview, and you don't have to read it all, but basically this is a summary of some of the different types of sensing technology that is used for explosives detection right now. This morning's talk was on an SPR device. I'm talking about microcantilevers. There's a bunch of ways to do this, and each have their pluses and minuses. So what I'm saying here is, for a particular application, there's not necessarily one good technology, but often the technologies will slot into the right applications. So how are we doing this? Well, we're combining this nonlinear sensing technique with molecularly imprinted polymers. So our colleagues at the ARL are using polymers that are templated here's the templating, molecularly imprinted polymers, which are templated for TNT, actually. We're not sensing TNT in our lab at UCSB, of course, but we are sensing DNT, which is similar. It's a precursor to TNT. But the polymers are templated for TNT, so essentially they're built with templates so that the TNT molecules prefer to bind there and not other ones. And I'll show you our results on that. So essentially in this device, this is a very simple proof of concept. We're actually using a micro beam. It's fixed on both ends so that it has the nonlinear behavior we want. We're not driving it with a parallel plate capacitor, although we can. These results I'm showing you really are just like the kid on a swing. We're taking a beam and we're using a piezo to shake it in plane, and that adds axial stretching to the middle of the beam and causes the same resonance behavior. The nice thing about this is you can drive the beam with a regular piezo in direct resonance at the same time, without changing anything else about the sensor, so we can compare linear to parametric sensing technology. So basically we use a permeation tube with the DNT in it. So you heat to a certain temperature, you know what concentration you're getting. You flow that into a chamber which contains the device. The chamber is at room temperature and pressure because, again, we want the sensors to work in the real world. So it's standard room temperature and pressure. We do that in this measurement. We do that sweeping technique that I showed you, that I explained already. So you run out in frequency, and then you step down, and when you hit the boundary, you put a mark, and then you test again. And I'll show you the time effects of that. So, and then we're reading it out with a laser Doppler vibrometer. We can also do this on chip, although with this experiment, because we were just trying to test out the molecularly imprinted polymer technology, we didn't. So the device is really simple. It's SOI fabricated. I won't go over that in detail. I'm happy to discuss it with anyone. It's very simple. And then we spin coat the polymer. We did both spin coat and inkjet coating to try and get the polymers coated. As you can see, it's a little messy looking. I'm not really happy with how this process has gone, so we're still improving that. But we do get the polymer on the devices, and that's another reason we made these devices really simple, so that if the polymer wasn't perfect, it wouldn't break the device or make it perform poorly. So this is a characterization slide. So here's what we really care about. Here's the sensor response. And we did, the top curve is a linear sensor. The bottom one is the bifurcation or the parametric detection. As you can see, the parametric detection is much less noisy. And the measurement is approximately the same. Notice it takes some time. We're doing this flow measurement. There's a lot of time constants in this stuff, and we're still decoupling all of them. There's the diffusion of the species into the chamber, and there's the binding onto the chip, and and then there's also the time related to the sensor response, which is not the limiting factor here, but still in a real world situation we'd like the sensor to operate better. But as you can see, we can detect the frequency down to a 0.44 hertz, and the frequency detection is the real coupled to the sensitivity. So what does that mean for sensitivity? Well, with these molecularly imprinted polymers, we can plot these Langmuir-Freundlich isotherms and get to a sensitivity which is good. I mean, it's the same kind of sensitivity they're talking about this morning, detection limits of sub-ppb. With the linear detection, it's 0.62. With the nonlinear device, it's 0.1 ppb. Now, it's reasonably reversible. We can do this over and over again. As you can see, it takes time for the device to unbind, for the species to come off. We're looking at ways to make the polymers so that they release the specimens quicker. We're also heating the device up and trying to optimize that so we can essentially clean the sensor in operation. We also did some selectivity measurements between DNT and toluene. These are and imprinted and non-imprinted devices. So the molecularly imprinted polymers, we did a control experiment where the polymers were not imprinted with DNT. Notice they do still respond. You'll get some nonspecific binding, but it's clear that the results are much better for the imprinted polymers for both resonant and bifurcation. And then this is the toluene versus DNT. Again, toluene has the same backbone as DNT, so it's a similar molecule, but not the same. And as you can see, the selectivity is better for DNT than toluene. So we're reasonably happy. We're still improving the polymer technology, and that's our goal for the next year or two, but we're definitely happy that they are selective. So in summary of the actual experimental results, we've been able to get sub-ppb detection limits, which we're very happy about, with some selectivity and reversibility. And the response time, again, we'd like the response time in the sensor to be better. And so that's what I'm going to talk about in the rest of my talk, is how we do that. So you have to think, when you're talking about nonlinear systems like this and detection of bifurcations or detection of a point in space, the location of this bifurcation or where the amplitude shifts. You have to think of noise in a different way, because noise now is, where is that thing in space, right? Brownian motion is going to cause it to move, that line to move back and forth a little bit, right? And how you come up to it, how you measure it, how can we tell where it really is, right? If we do that detection method where we step frequency, we start here and step, 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 step. How many steps you take, what size those steps are, how fast they are, those all matter. Because if there's one thing that probably all of you already know about nonlinear systems, is that time history matters. Initial conditions matter. If you come at something from two different initial conditions, you get a different result. So if you sweep, so you can have, depending on how you do the measurement, you can delay the bifurcation. So if you sweep really fast, you can sweep faster than the time constant of the system and get past it before it jumps. If you sweep really slow, you can have Brownian motion hit you up before you're really there. So what's optimum, and how do we do this? And so at first we thought there would be an optimum sweep rate. And we did some analysis on this, and we found the optimum sweep rate for different noise parameters. I'm not going to talk about it today because we discovered something else that worked a lot better and kind of overshadowed it. So, but again, what we want to do is look for some other way of detecting this boundary. And how do we do that? Well, what we want is, we have a pretty good model. Okay, the device, the nice thing about MEMS, you can build them reasonably clean, reasonably simple. So the model works. We have a lot of faith in the model. And we want to look at what happens right before the device bifurcates. Okay, so when you come up, there's some time constant. When you're nearby, you're sitting right at the bifurcation. There's some interesting things that happen. We wanted to take a really close look at those and see if we could use any of those to improve our sensing modality. So it turns out when you get close to these devices, so you sweep in, when you get really close to this, an interesting thing happens to the phase of the system. So the phase noise has one value. And then when you get very close to this system, basically when you're at the point where if you wait long enough, it will in fact bifurcate, the phase noise squeezes. And from a mathematical perspective, you can think of that as squeezing. The phase noise is squeezing along one manifold and increasing along another dimension. And it has a special time scale. And I won't go into the mathematics, but basically what that means is that there's this interesting phase squeezing that happens. So this is the phase noise of the device. This is as you're getting closer and closer to the device, as to that bifurcation point. So this is the phase noise. And then when you get close to the device, the phase noise squeezes down by between 2 and 3 orders of magnitude. And then at some point it bifurcates and you get the shift. And this green period is this period. And look at it, it's 8 seconds. It takes 8 when you're really close to the device, so the closer you get, the longer it takes to bifurcate. So it takes 8 seconds, you have this slow squeeze, this phase noise squeeze. So for that tells me that that's slow enough that you can use an FPGA controller with very little computing power and build a circuit that can maintain the device in feedback at that point. And so that's what we did. So here's the test setup. Again, we use the vibrometer. Again, because this is so slow, we didn't have to have attendant electronics. The computing power was had to be reasonably high, but the time of the computing didn't have to be reasonably high. So we could use the laser vibrometer as a detection mechanism instead of having to build an on-chip one. We approach the snap-on, and then we lock in, using a lock-in amplifier, we lock in at that point. And then we are able to maintain the device without bifurcating and track the bifurcation. And so now all of our problems of the earlier thing went away. We're not changing the initial condition. We're right at the bifurcation. It's in a very slow time scale event, and we can maintain that small phase noise, which means we're holding the device right at the edge of instability without ever bifurcating. The device never fatigues. The device never moves, essentially. It doesn't move. It just sits there in white noise. And you can get very, very high sensitivity. So this is what the probability distribution of the phase noise looks like when you're outside of that point versus when you're inside. Again, 2 orders of magnitude improvement in the phase noise. Here's what it looks like as you approach. And then how does this look in terms of how much data you can get in the actual measurement? So again, the device isn't moving. When it's locked in, the movement is about 140 picometers, which we can measure with the laser vibrometer, but it's barely above the white noise, the Brownian motion noise of the system. When you're at approach, it moves a little bit less. So it's moving a little bit, but not very much. This is what the lock-in of the phase noise looks like. A corresponding linear sensor would be moving at about 340 nanometers, and if it bifurcated, it would be moving at 3 microns. So that's just the amplitude scale. And so now let's compare this to our other sensing technique. And how much data we can get, because as you know, with a sensor, the more data you can collect about a point, the better your understanding of for any stochastic event. The more data you get, the better you understand it. So you want to be able to get lots of data points quickly. So, for example, if we did the frequency sweep, if we wanted to get 1,000 points to get this kind of accuracy, it would take us 500 minutes. Well, that's completely not useful in the real world. the same thing, we can get 20,000 points. So that's another 20 times more data points in 150 seconds with the noise squeezing control. Okay, so now we're talking about a sensor where you actually can get something useful in a very little time. And also the device you're not stressing the device, you're not subjecting it to these large amplitude resonances, and you're still using the benefits of the nonlinearity. If you use, I didn't talk about sweeping voltage, so I'll skip this, but if you want to compare this directly to the linear device, on a linear device, you would have to drive this to an amplitude of 650 nanometers to get the same amplitude, and the time is actually faster with this device, and it's only moving 120 picometers to get that same sensitivity. So we're really pretty excited about this technique, and so in conclusion, I want to just say that the noise squeezing control is really making these nonlinear sensors, I think, a lot more useful from a time perspective and from a measurement perspective, because this kind of circuit is easily implementable. It's just like building a circuit to track amplitude. It's a simple device, simple type of sensing to implement. The avoidance of having to wait for the actual blow-up allows you all the benefits of the nonlinear device without actually having to wait for the acquisition for that to occur, and also the uncertainty with the nonlinear system and initial conditions. I didn't discuss the benefits of the steep slope on the Arnold tongue, but there's even another reason that these devices can be more sensitive than linear devices. So it's even before we implemented this, the nonlinear sensing was giving us better results than linear sensing for the explosive detection. And I think right now we're currently implementing this on the explosive detection setup. And I was hoping to have results for this meeting. Unfortunately, we didn't quite get the experiment set up in time. Our partner at ARL is out on maternity leave, so it's kind of slowing things down, but very exciting for her nonetheless. And so hopefully I'll have results on this pretty soon. And then other application areas for nonlinearity. Previously I've discussed, I have done some work on inertial sensors in the past on building a gyro that was immune to fabrication tolerance problems, because we use this wide band of actuation to be able to tune the drive in the sense modes. Also at AFM, we're working with AFM, doing a lot of AFM applications using nonlinear coupled oscillators. We're doing some stuff in RF right now. So there's applications to lots of different fields, not just the mass detection that I've discussed today. And I'd like to acknowledge this work today was the work of two of my former PhD students, Chris Burgner and Z Yi, and Ellen Holtoff at the ARL. And then these are just other students in my lab and former students who of course, have contributed to this work some way or the other over the last 15 years. So also some of the analytical work, we've partnered with Steve Shaw from Michigan State and Jeff Rhodes, who was Steve's student at Michigan State, who's now an associate professor at Purdue. So they also figured in heavily in this work. So with that, I will end and be happy to take your questions. Thanks.
Okay, thanks so much. Very nice work. I thought I could see nonlinearity. My question was, and I've forgotten the okay analysis of these kind of oscillators a little bit, but
yes, you can, indeed. You don't need the nonlinearity at all. We built in the nonlinearity because the nonlinearity governs the final amplitude you can get. And if you have a very nonlinear system, the amplitudes can get so large that the devices break, or they bang on substrates and things like that. So, but certainly, you can get parametric resonance with a linear device. You can make almost any device do this if there's a time-dependent stiffness.
Great work.
Thanks.
I have two questions regarding your parametric collaborations that you have with ARL. Can you elaborate a little bit on the importance of the thickness of the polymer and how crucial that is for the sensitivity and how they control it? And then you also mentioned the cleaning process that makes the device reusable. What are the thoughts on that?
Okay, so it's a very good question, and it's a question I don't have a complete answer to. This is a very relevant ongoing work. Now, the deposition of these polymers I'm not happy with at all. They deposit them and then mail them to us, and we look at them, and some of them don't have any polymer on them, and some of them have really essentially what I would characterize as blobs of polymer. Now, the devices function regardless. If there's any polymer on there at all, they function. But I would like it to be much more uniform. Yeah, we measure the coverage and we measure the uniformity, and it's just we haven't been able to do a comprehensive study because we haven't had enough devices that had good uniformity. So I can't say for certain, but it's definitely something we're currently working on, and that's ARL's priority, is to try and nail that down, trying to get better. The technique they use, essentially we found the best results with just spinning it on, but even that doesn't work that well. The inkjet I thought would be nice because we could put it in the middle of the polymer, but that doesn't work either. That was very spotty on whether they would get within 100 microns of the device. So that's a big deal. As far as the cleaning of the device, the heating it up speeds up the reaction. So we purge in between cycles. You purge with nitrogen, and they do unbind after time. However, if you test the device if you use the same device for days on end, it will saturate, and then you have to clean. You have to heat it up. You have to purge. Even doing some actual chemical processes to it make it better. Again, we're trying to work on some new polymers that unbind easier because they don't have to stick hard. They just have to stick long enough for you to measurement. So we'd like them to be a little less tightly bound. Sure.